Okay, so shall we start, David?
When you're ready.
All right. Welcome, everyone. Welcome to Harvard University Center for Mathematical Science and Application, CMSA, Quantum Matter in Math and Physics seminar series. Today, we are very honored to have the presumably last talk of this 2020 fall term. And we have the great honor to invite Professor David Tong from University of Cambridge to telling us an exciting story. He recently has done the work, the gap Chiral Fermions. And let's welcome David Tong directly. Please.
Thank you, Juven. Thank you for inviting me back to the seminar series. Again, thank you all for turning up. I'm sure many of you have had a very stressful semester teaching, so I'm very grateful that that you've come here. I'm going to tell you about a very simple question in quantum field theory. And much of what I'm going to say relies on very old and classic work in quantum field theory, dating back to the 80s and 90s. The question is really straightforward. And it's just this. Take a bunch of massless fermions and give them a mass. And the question I want to ask is, what symmetries are broken and which symmetries are preserved when a bunch of fermions get a mass? It's a question that came to my attention over the past few years, primarily because of the developments in condensed matter physics, in topological phases of matter in particular, starting with the work of Witkowski and Kitaev 10 years ago. And then this work has been developed over recent years, primarily getting a better understanding of anomalies and anomalies associated to discrete symmetries. But here I'm instead just going to talk about continuous symmetries in 4 dimensions. There are some very interesting stories about discrete symmetries. It's just here I'll focus on continuous symmetries. So the goal is to give you what I hope is an overview of some results about this question in the first half of the talk. And then in the second half of the talk, I want to change gear a little bit. And I'm going to talk about the question of how you put chiral fermions on a lattice, because it's a question which many speakers in this seminar series have a healthy obsession with. In particular, David Kaplan gave a beautiful overview of this a couple of weeks ago. And I think the results that I'm going to explain here have some bearing on that broader question. All right, so this is the question. Let's just set the ground with something that hopefully everybody knows. In 4 dimensions, just take a single free Dirac fermion. And if that Dirac fermion is massless, then there are 2 U1 symmetries. There are 2 U1 global symmetries because a massless Dirac fermion splits into 2 Weyl fermions, a left-handed and a right-handed piece. And at the classical level, actually at the quantum level for a free Dirac fermion, you can act with U1 symmetries independently on the left and the right-handed Weyl fermions. However, if you give the fermion a mass, the chiral symmetry or the axial symmetry, that's the one that acts differently on the left and right-handed fermions, is broken, while the vector symmetry survives. So at a very naive level, you might think that the answer to the question on the previous slide, what symmetries survive when a fermion gets a mass, is, well, vector symmetries survive and chiral symmetries are broken. And that's partly right, but not really. There's a deeper reason for why symmetries get a mass, and it's not just that, for why symmetries are broken, and it's not just that they're chiral. The deeper reason was understood 40 years ago. It was understood by Toft, and it goes by the name of the Toft anomaly. So this is the deal. Take a global symmetry G, and as I said, this is going to be a continuous symmetry for the purposes of this talk. For every quantum field theory with a global symmetry G, there's a number that you can associate to that, which is the Toft anomaly. And the number is very easy to compute. You just compute the sum of these triangle diagrams where you sum over all fermions running in the loop with 3 global currents associated to the, or attached to the edges of the triangle. If the anomaly is non-vanishing, it's not terrible news for the symmetry. It's not like the symmetry doesn't exist in the quantum theory. What it means is the following. Firstly, if the Toft anomaly is non-vanishing, it's not possible to promote this global symmetry to a gauge symmetry. It's not possible to gauge the symmetry. That's the real meaning of the 't Hooft anomaly.
David, I'm sorry to interrupt, but why you call it 't Hooft anomaly? Because the one triangle anomaly, it was I would call it Adler anomaly.
You would call it the
Adler, because Adler was the one who went forward with this triangle anomaly, right? Right. So
it's important to distinguish these
two. That's what I'm sorry to interrupt, but
I'm very pleased to. So the ABJ anomaly, the Adler-Bargy anomaly, that's when you have one global current and two gauge currents.
Okay.
If that's non-vanishing, it kills your symmetry. If that's non-vanishing, your symmetry is not a symmetry of the quantum theory because the divergence of the current is equal to trace of F wedge F. That's the ABJ anomaly. In contrast, the 't Hooft anomaly is when you have three global currents. If the 't Hooft anomaly is non-vanishing, divergence of currents is still zero in the quantum theory. It's non-zero if you turn on background gauge fields.
Okay. But I agree. But but when you consider original ABJ anomaly, it's it's a little bit conditional because the same gauge current could be viewed as global as well. That's why there is overlap.
What can I tell you? The anomaly is a deep idea that appears in many different guises in quantum field theory. I think somehow this is the most basic, though. The 't Hooft anomaly is the most basic, and other things then follow from this. A few years ago, I wrote some gauge theory notes where when I introduce anomalies, I say an anomaly is a classical symmetry which doesn't survive quantization. I'm not happy with that characterization anymore. I think that starting from a 't Hooft anomaly is a better phrasing of what an anomaly is really about, and then that subsequent statement follows later. All right, so we have a global symmetry. It has a 't Hooft anomaly. What do we know? Firstly, you can't gauge that symmetry. Okay, maybe you didn't want to gauge it. But more importantly, it tells you something about the dynamics of the quantum theory. Because the important thing about this 't Hooft anomaly is that it doesn't change under deformations of the theory that preserve the symmetry. And moreover, it doesn't change under RG flow. So if you start from some weakly coupled theory that has a symmetry G in the UV, it has an anomaly. A question that we very much like to ask in quantum field theory is what happens as you flow to the infrared? This gives you a very good handle on what happens. Because if the 't Hooft anomaly is non-vanishing, then you know for sure there have to be massless particles in the infrared. The reason is the following, that if the symmetry is unbroken, then this 't Hooft anomaly has to be reproduced in the far infrared. And the only thing that can reproduce it is massless fermions. So you know for sure there has to be massless fermions in the infrared which saturate the 't Hooft anomaly. In contrast, one way out is simply that the symmetry is broken under RG. But if the symmetry is broken, you're guaranteed to have Goldstone bosons because this is a continuous symmetry. So it's a very powerful statement. You do an almost trivial calculation in the UV to compute the 't Hooft anomaly for a global symmetry. It tells you immediately whether or not it tells you immediately that there must be some kind of massless particle in the infrared. All right. Any questions, by the way? I'm very happy for people to jump in and ask questions.
Question?
Yeah, please.
So when you say it must be, I understand it must be something massless. When you say it must be massless fermion, it could be a CFT, right? Where it's hard to say what.
Yeah, that's right. It could be. Yeah, a better statement would be if it's something free in the infrared, it's a fermion. But you're right. It could be something interacting. But what to say? It's hard to say, but I don't think it could be a bosonic CFT, and there has to be some fermionicness to it. Hi, Max, by the way.
Hi, David.
It depends whether you have a spin structure, requires spin structure.
Yeah, of course, in the UV you have a spin structure, so it's a somewhat moot point, but because you have fermions.
Probably depend on the theory, right? Maybe some UV doesn't require spin structure.
Oh, you could do, a spin C, spin SU2, the kind of things you were discussing.
Yeah, but say returning back to ABJ anomaly, for example, that say you can prove spontaneous breaking, using ABG and consistency condition, right? that in this way, but it would be not about massless fermions. It's about massless Goldstone particles, right?
That's right. So that was Toft's beautiful argument, using Toft anomaly matching for why in QCD the continuity has to be broken in the infrared, because the other assumption that it was unbroken meant there have to be massless baryons, but the baryons couldn't saturate the Toft anomaly.
No, it could be not just massless baryon, it could be a pair of opposite parity, but consistent. His condition shows that it's not the case in QCD. Generically, it could be not different.
You assume confinement, so it has to be a massless fermion, but the fermions, the mesons don't do it for obvious reasons. So it has to be something with an odd number of quarks. So okay, if I call those baryons, then maybe it is true. Okay, so the question I'd like to ask in this talk is, what if you have a symmetry G where the Toft anomaly vanishes, but it vanishes in an interesting way? And let me give you a few examples. A bunch of fermions, massless fermions, with a global symmetry G, with the following matter content will do the job. If you don't remember young tableau, 2 boxes horizontal is the symmetric representation, and 2 boxes vertical is the anti-symmetric representation of SUN, and a single box is the fundamental, and putting a bar over everything means you take the conjugate representation. So this is a bunch of famous chiral representations where nonetheless the anomaly vanishes because of a balancing between the different reps. So the first one is SUN with a symmetric and a bunch of anti-fundamentals. The next is SUN with an anti-symmetric and slightly fewer anti-fundamentals. And the final one is of course the most famous of all. It's SU3 times SU2 times U1 with 15 fermions that carry the quantum numbers of quarks and leptons of the standard model. And if you don't remember what they are, I'll tell you a little later in the talk. Was there a question? I heard a little bubble.
By the way, David, I think every symmetry, well, including the space-time, there's a spin group, spin D times all this group. Is that right?
That's right. So these are going to be
and spin times SU3 times SU2 times U1. No problem. Yeah, please go on. Thank you.
So are these wild fermions or left or right-handed?
Thanks, Subir. No, that's really important. And I should have said each one is a vile fermion, and let's take them all to be, say, left-handed. When
you take the conjugate, then they're right-handed.
That's right. In 4 dimensions, in contrast to 2, if you take the conjugate, you get the conjugate rep with a right-handed piece. So in the first one, there's a left-handed symmetric, but that means the conjugate of that is a right-handed conjugate symmetric. Anti-symmetric means something different. A right-handed conjugate symmetric. Does that make sense? I'll take that as a yes. All right. If you've seen these before, and all of you have seen the third one before, but if you know a little bit about gauge theories, it's likely you've seen the first 2 before as well. You've almost certainly seen them in the context where G is a gauge symmetry. Of course, a prerequisite to have a chiral gauge theory is that the anomaly vanished precisely so you could gauge G. At least for the first half of this talk, I think it's going to be pedagogically useful to think of G as a global symmetry. I'm going to stress G will be unbroken throughout the whole talk. G will be anomaly free throughout the whole talk. Should you at any stage wish to gauge it, please just go ahead and do so. But it's going to be a bit more useful to think of G as a global symmetry, simply because if you gauge it, it comes with strong coupling scales, and you're going to have to ask how those strong coupling scales compare to other things and so forth. So the first half of the talk, we're going to...
But David, it is then rather not about how to call it gauge or global, but what kind of current you are using for your triangle, right? Because if you are using gauge current, or you are using, kind of something else than a gauge current, right? So in this way, you didn't formulate specifically for these cases, what kind of currents are there, gauge or not gauge, right?
Not gauge.
Not gauge, right?
Not gauge, global, yeah. Okay. All right. So this is the goal of the talk. Take a bunch of massless fermions sitting in these global representations of a global symmetry. Try to give them a mass, but try to give them a mass without breaking the symmetry G. That's the game. And it should be obvious because there's no conjugate representation, so you can't pair them together. Any bilinear would break G.
But you see, when you're saying without breaking gauge symmetry, you are then not implying then you're using this gauge currents as the currents in your triangle, right? Still.
No, G is a global symmetry.
Okay, but say the last one, it's a global or SU3 cross SU2 cross U1. Is it global or gauge? It's both, right?
It would avoid confusion if you think about it as global for now. But if you insist on thinking about it as gauge, please go ahead and nothing bad will happen. But I think global would be somewhat easier to think about, which of course is unusual for the standard model, but we'll see. But you know, within the context of the standard model, the question applied to the third one is, can you give a mass to one generation of the standard model without breaking electroweak symmetry? And the answer is yes, and I'm going to show you how to do it in this talk.
Maybe.
All right.
Is that true that the last one example, the standard model, also work when you model a ZQ, Q is 1, 2, 3, and 6?
Yeah, it's independent. If you gauge G, there's a question about the discrete global thing, and yes, it's independent of whether or not you mod out by, say, Z6.
The conclusion all apply, I believe. Yeah, no problem. Please go on.
All right. So what are we going to do? It's useful to have these in mind, and I will go through each of these examples later, show you how to do it, but let me just give you the basic idea. So we have a bunch of massless fermions realizing some non-anomalous global chiral symmetry G. What are our options? You can't write down a bilinear term, because a bilinear term would break G precisely because this is a chiral representation. So a standard mass term is out. You could write down 4 Fermi terms, but 4 Fermi terms in 4 dimensions are irrelevant. So they're not going to affect the theory in the infrared, and in particular, they're not going to achieve what we want, which is to give all the fermions a mass. So what we're going to have to do is, in addition to the fermions, the massless fermions transforming under G, we're going to have to bring in some extra degrees of freedom. And I'll walk you through what properties these extra degrees of freedom have. But roughly speaking, here's what we want. We want the extra degrees of freedom to transform in a vector-like representation of this symmetry G. The idea being that first, they do not affect the anomaly for G, so everything still remains non-anomalous. And secondly, it's going to be trivial to take these auxiliary degrees of freedom, give them a mass, leaving G untouched, and leaving behind the massless fermions that we care about. So it's very easy to decouple the auxiliary degrees of freedom. However, what we're going to do here is bring these auxiliary degrees of freedom down, allow them to interact with the massless fermions G, such that when you flow to the infrared, everything becomes massive, but G remains unbroken. That's the goal. Let me fill you in a little more details about these auxiliary degrees of freedom. They're going to come in 3 kinds. As in usual continuum quantum field theory, we'll have scalars fermions and gauge bosons. Each of them has some caveats associated to them. Let me tell you what they are. We can add scalars into the game. The scalars can be charged under G, because there's no problem in giving bosons, spin 0 bosons, a mass without breaking G. However, if you do introduce any scalars that are charged under G, you better make sure they don't condense. Because if they condense, they break G, and spontaneous breaking of this global symmetry is just as bad as explicit. So that's the caveat with the scalars. You can add fermions, additional fermions. In many examples, they won't transform under G at all, but when they do, they have to come in left-right conjugate pairs. Because obviously it would be cheating if I took a chiral representation, added the conjugate representation, gapped everything, and declared success. That's not allowed. Any new fermions you add have to come in left-right conjugate pairs, simply so you can give them a mass and decouple them, should you wish. Finally, gauge fields. And let me remind you that the goal here is to drive some strong coupling effects, which are going to give these fermions a mass. And in 4 dimensions, if you want to drive strong coupling in the infrared, your only real option is to do it using non-abelian gauge fields. And so we will introduce gauge fields to do the job. We're not allowed to gauge this symmetry G. Okay, G you should think of as a global symmetry, and it should remain a global symmetry everywhere throughout the story. What that means is that if you want to introduce some new gauge fields, you have to identify an additional symmetry that I'm going to call H. You can gauge this symmetry H, provided it's non-anomalous, but it has to have some properties. Firstly, H should commute with G, and secondly, there should be no mixed anomalies between H and G. That ensures that when you gauge H, you don't mess up G. G remains a genuine global symmetry of the system. And finally, I said that all this auxiliary stuff, we want a way just to decouple it and make it massive so we can return to the phase with just the massless fermions. And the way we do that for gauge fields is we introduce scalars that are charged under H that allow us to Higgs it and just decouple it. So whenever there's an H gauge field, there should also be scalars that allow you to remove it, should you wish. Okay, so these are the rules of the game. I hope you agree that they're reasonable. They're roughly speaking the rules that people talk about when trying to classify different topological phases of matter. This is more or less where I got them from. All right.
Maybe?
Yeah, who's speaking? Xiaogang?
Ruben. No. I was.
Hi, please go ahead.
Many people. Okay, let me say first. So it's clear that G does not have total anomaly, and also G and H does not have a mixed anomaly.
Right.
But does H can contain anomaly in your?
No,
No.
You couldn't gauge it. So
You want to gauge H. Okay.
yeah,
So there is no anomaly in G in H. Also no mixed anomaly between G and H.
right. There may be other symmetries that are anomalous, but I don't care about them. But yeah, G and H have to be anomaly free, and we'll see. We have to bend over backwards a little bit to achieve that for H, but we'll do it.
And will there be example H contain G as a subgroup?
No.
No. Okay.
A different symmetry. Yeah, you're not allowed to gauge G.
Okay. Good. Thank you.
Yeah, I have a question here. So indeed, you have very nice general setting with the scalar fermion and additional gauge field. I just wonder why you need so many. Just adding charged scalar may be enough. Is that, I wonder what's your opinion on this.
So it's 4 dimensions, and I start with free theory in the ultraviolet, and I want to flow to strong coupling in the infrared. So I want relevant deformations. Yukawa interactions in 4 dimensions aren't relevant; they're marginally irrelevant. So they don't do the job. They could do the job in 2 dimensions, but I'm talking about 4 dimensions here. So you're obliged to introduce non-abelian gauge fields for this to fly.
No, the reason I ask is the following. You know, in condensed matter, we have this pseudo gap phase from preformed Cooper pair. And here one can do the similar thing that you can introduce a scalar and the Higgs mass. And then scalar form nonlinear sigma model and actually became a disordered symmetric state. But somehow the Higgs mass maintain if this nonlinear sigma model have a long correlation length. And so this is a way, actually in condensed matter, high T superconductor, this is a way to output in pseudo gap phase. You have a superconducting gap from D wave, but somehow the other parameters are disordered. So you don't really have a superconductor, but you have a very stringent metal. Here, maybe one can do the similar thing that using Higgs field to obtain the mass gap. And then if the Higgs field from nonlinear sigma model became disordered with a long correlation length, and we hope the mass gap remain, but the symmetry was restored. So this is one approach by just introducing scalar without introducing new fermion and new gauge field. Yeah.
I think that this difference in perspective between condensed matter and continuum is really going to be sort of the key as this talk progresses, and in particular in the second half. So it's a true statement that if I work in the continuum and I just have fermions plus scalars, I will not drive to strong coupling in the infrared. But in condensed matter, you guys have something that we don't, which is an underlying lattice.
No, the fermion scalar coupling, it became relevant if a scalar have a condensation.
Oh, I see. But then in the
But then the next thing is the trick. We say this condensation only happen at a certain length scale. At a very long length scale, the condensation disappear because of a fluctuation and disorder. But however, at the length scale much bigger than cutoff, the condensation is still there. which provide a gap, Fermi gap. So there's a two stage. So there's an intermediate length scale, which is between cutoff and the low energy, so this is basically what people do in the pseudo gap phase of a superconductor. One idea.
I think it can't happen in 3+1 dimensional gauge theories. In the 3+1 dimensional field theories in the continuum. You might be able to do it on the lattice by turning on strong coupling effects at the lattice scale. But I think in continuum field theory, in 3+1, this isn't possible. Lower dimensions, sure, because you can have strong infrared effects. But
why is it impossible? Because the reason for that is following. At a certain intermediate length scale, we simply have a Higgs phase. Then we can integrate the fermion, which is capped by Higgs mass.
In the Higgs phase, you've broken G. So at that stage,
yeah. But however, you're obtaining an effective nonlinear sigma model of a Higgs field, which turns out to be go into the fluctuating symmetric phase at even longer scale.
But a nonlinear sigma model in 3+1 dimensions is just trivial.
Yeah, I agree. At this stage, one introduce strong coupling indeed. So therefore, at this length scale, which gap the fermion, the resulting nonlinear sigma model in the strong coupling regime, which at a lower energy, which flow to the symmetric phase. Yeah. So indeed, this is non-trivial RG flow, and yeah. I'm sorry for interrupting. Yeah,
not at all. But there is a key point that you can do things in condensed matter physics that we can't or don't want to in a continuum quantum field theory, and this because you have an underlying lattice and you can have strong coupling at the lattice scale, and this may be one of them.
No, let me. I think
I actually don't understand that distinction. I think whatever they. Sorry, go ahead.
I'm sorry. Yeah, I think this is within field theory. That is a field theory of a nonlinear sigma model can have a symmetric phase, even when even in a sense where correlation length is much longer than cutoff scale. That means the field theory is okay. And even such a field theory, a nonlinear sigma model for such a field theory, I think do allow a symmetric disordered phase, which are fully gapped. I'm sorry, Nati. Sorry.
Nati, you had a comment.
I think you're actually saying the same thing. So I don't know. My problem is I don't see what the distinction is. And my understanding is that whatever you can do on the lattice, you can also do in the continuum at the cost of adding more fields.
I agree with you, but the important part is important. Sorry, the last part is important. You need extra fields.
Okay, so you add more fields, who cares?
Yeah.
But then there's no, you're really saying the same thing. The only comment that you need is to allow David, first of all, you allow David to continue to talk. But the other thing you should allow David to do is to add as many fields as he wants.
But they're going to include non-abelian gauge fields.
Yeah, I have no problem with that.
Unavoidable. Yeah, I didn't think you would, Natty, but I think it's unavoidable in 4 dimensions. Let me move on.
David, can I just ask about the last bullet point real quick?
Yeah, who's talking?
Max Zimmet.
Hey,
Hi. Why do you need the Higgs mechanism to gap the gauge field? Can't you rely on confinement?
If it confines, it's because it's strongly coupled, but it's strongly coupled and interacting with the massless fermions that I want to keep massless. Confinement will play a role very shortly on the next slide. But what I want to be able to do is decouple this gauge field H so that the massless fermions remain as they were originally, massless and untouched. And that really needs the Higgs field.
Sorry, I cannot avoid, this is Eduardo Fradkin, I cannot avoid for asking an old question. In what representation are your Higgs fields? Are in the fundamental representation?
Yeah, I'm going to put them in the fundamental. They're mostly going to be in the background, but I think SUN, N Higgs fields in the fundamental will do this.
I mean, but do they kill, I mean, if in that case you have the problem that there is no distinction between confinement and Higgs, as we have a long time ago.
So what I'm really going to do is when I want this confining phase, I'm going to take my my Higgs fields and I'm going to give them a mass which is much bigger than any other scale. So just decouple them for the role of confinement.
Okay.
Yeah. All right. So let me tell you what the basic idea.
Sorry to interrupt again, but he doesn't have the center acting anyway. So the scalars do not mess up anything because you already had fermions in the fundamental representation.
That's
so
right.
adding the scalars is not going to affect that thing.
Okay.
So here's the key idea, which I'm going to illustrate with a number of examples. If you can find some gauge dynamics for the new gauge group H, under which the group that we cared about originally, G, is a global symmetry. If you can find some gauge dynamics for H so that that gauge theory confines without breaking chiral symmetry, the chiral symmetry being G, then that's very easy to turn on its head a little bit and find a way to gap the fermions without breaking G. So this is the key idea. It's a very simple idea, and I'm going to illustrate it with a number of examples, but the basic idea is the same in every case. Find an H that confines without breaking chiral symmetry. Now, as I'll explain as we move forwards, I know of two classes of gauge theories that have this property, confinement without chiral symmetry breaking. The first is when H itself is a chiral gauge theory, and the second is when H is part of a supersymmetric theory. Doesn't have to be chiral in that case, but there are examples first discovered by Natty in which supersymmetric theories confine without breaking chiral symmetry. As I'll explain in the next few slides, whenever you have an H which does this with some matter content, then you can turn that on its head and find a way to gap a bunch of chiral fermions without breaking G. That's where we're going with a few examples as we move forwards. All right, example number one, and I'm going to do each of those three examples that I showed a few slides back. As we'll see, each of them is sort of similar, but each comes with a slight twist that needs discussing, hence the need for three. So example one is the easiest. We take a bunch of massless fermions with a global symmetry G. The fermions transform in the symmetric and a bunch of anti-fundamentals. There's n+4 anti-fundamentals. All right, what do I want to do? First thing I want to do is find some new symmetry group H to gauge. And it's totally obvious what I should do because I've got n+4 anti-fundamentals, so I can just gauge the symmetry that rotates them. So there's an H equals SU n+4. On its own, that H would be anomalous because it's just a gauge group coupled to a bunch of fundamental Weyl fermions, n fundamental Weyl fermions from the perspective of H. So I need to cancel the anomaly. And the way I cancel the anomaly is in...
What exactly is your starting point? I thought your starting point was a system that has this spectrum of fermions and the global symmetry with G, which was SUN.
Yes.
Nothing else, no other global symmetry.
Right, so I said I could, I've maybe done the logic a little backwards here, Natty, but I said I could add a bunch of extra fields. The extra fields I'm going to add are a bunch of singlet fermions under G. The singlet fermions are going to transform in the anti-symmetric representation of H. In other words, I want to add an additional 1/2 times n+4 times n+3 singlet fermions under G. That was allowed in my my list of things.
But you said that you're going to gauge the SU n+4 under which the anti-fundamentals are charged.
That's right, but this commutes with G and it has no mixed anomaly with G.
Right, but what that means is that your theory before you started adding field has a larger symmetry than G.
That's right, but there could always be other symmetries. I don't care if I lose them along the way.
Okay, so you are allowed to break this. So, but it could be that these fermions were massless because of anomalies associated with larger symmetry.
Yeah, there could be other things, but
okay, now I understand. Thank you. Sorry.
Yeah, G is enough to ensure that you know they're gapless at the bilinear level, the quadratic level. Yeah. So I've gauged this H. I should add some scalar fields, as we've said, to make sure that I can decouple H. Once I've added the scalar fields and I Higgs H, I can get rid of all the extra stuff. So there is a limit where the scalar fields condense, where all of this auxiliary stuff goes away, and I'm left just with the massless fermions that I started with. However, the other limit is to give all these scalar fields a very big mass, positive mass squared. And in this case, I've got some work to do because when the scalar fields are massive, they decouple. But now I have a bunch of fermions that have quantum numbers under a non-abelian gauge symmetry, and I have to figure out what that non-abelian gauge symmetry does. All right, so here are the fermions with some names given to them. The original guys that were in the top of the slide are given names lambda and psi. And the first element in the bracket tells you how they transform under G, the global symmetry, and the second element tells you how they transform under H, the gauge symmetry. And in addition, I've added these chi tildes. These are these extra guys that are just charged under H. So at the end of the day, I've got quite a well understood gauge theory. It's SUN plus 4, but it has a bunch of fundamentals and it has an anti-symmetric. Now, we're not entirely sure what this gauge theory does, but I think we have a pretty good idea. This was discussed quite a lot in the early 80s. And the best guess, which I think there's a reasonable amount of evidence, is that this theory has the property that we want, that it confines, H confines, but without breaking the global symmetry G. Now, from the perspective of H, the gauge theory, G had an anomaly, a Toft anomaly. It had a Toft anomaly because lambda is a bystander according to H. H doesn't know about lambda. So the whole collection of fermions didn't have a Toft anomaly for G, but if you just look at the psi's on their own, they do. So the gauge theory for H has a Toft anomaly due to the absence of lambda. And therefore, if it confines without breaking the symmetry G, there has to be a massless fermion in the infrared, which soaks up that Toft anomaly. There is happily a very, very nice candidate for the job. This 3 fermion composite, which I'm going to call lambda tilde, saturates the Toft anomaly for G. So the conjecture is that this theory flows in the infrared to just a single, I guess really a bunch of massless fermions. They're composites from the perspective of the UV, and there's a bunch because they transform in this symmetric representation of G. So let me tell you the evidence for this. One piece of evidence is, thanks Xiaogang, we can come back to the nonlinear supermodel later. One piece of evidence is just that it's a very simple scenario that ticks all the boxes. The next piece of evidence is something which I think somewhat grandly was called complementarity back in the 80s, but it's the following idea, that if you take a gauge theory like this, another possibility for the dynamics is that you get a fermion bilinear which condenses. Fermion bilinear is a scalar which condenses. Because this is a chiral theory, any scalar that you make out of 2 fermions is charged under the gauge group H, and so with Higgs the gauge group H. And with some fairly reasonable assumptions about the way these bilinears form, you can show that if that happens, you get the same result at the end of the day, that H gets Higgs to a smaller group, that smaller group confines, but it leaves behind one lonely quark, and that lonely quark has exactly the quantum numbers of lambda tilde. Finally, there's a very nice large N analysis, which shows that it's very difficult for the symmetry group G to break at large N. It's difficult to find the Goldstone modes. So the upshot is that I think we have very good evidence that this is the behavior of this particular chiral theory. With this in mind, we're basically done. We go back to the original theory and we introduce the following 4 fermion coupling in the ultraviolet. It's a 4 fermion term, so it looks irrelevant when you first look at it, but it's an example of a dangerously irrelevant operator. Because as you flow to the infrared, 3 of these fermions pair up due to confinement, and in the infrared act effectively as a single fermion field that I've called lambda tilde. And the upshot is that in the infrared, we're left just with this 4 fermion term becoming this fermion bilinear, but this is just a mass term that couples lambda to this composite lambda tilde. The 4 fermion term preserves G, so the upshot is we have a very simple system that gives a mass to all the fermions at the top of the slide, but preserving G. Very straightforward. This same idea is going to just hold in the next couple of examples, but as I mentioned, that there's going to be some twists. Any questions about this? Yeah, Juven.
This example assumed the dynamics from the work of Susskind and some other people.
That's right. So where was the magic? The magic is in the dynamics of this strongly interacting gauge theory, which we don't understand for sure, but this is our best guess. We'll see some things later where we understand them much better, but for now.
So this is what they called Technicolor at one time, right?
Not quite, Eduardo. Technicolor is a little different. It's where a symmetry breaks, but it breaks because of a condensate, because the scalar field is a Fermi bilinear. Here it's a slight twist. We don't want the symmetry to break. We're working very hard to preserve the symmetry. So it's related, but it's not quite the same thing.
It seems to me that from the point of view that you take here, you don't really need the assumption of the dynamics, because you can throw in another scalar. The other scalar will have with the quantum numbers of the condensate that you wanted to postulate, and then add some potential such that this scalar condenses, and then you can do almost everything at weak coupling.
No, if the scalar condenses, I break G. That's the concern. I've got to make sure G is preserved.
But it's the same thing as you did for the dynamics. I'm not changing anything, just adding a scalar with the quantum numbers of the condensate that you wanted, and add coupling such that it couples to it. And then whatever you achieved with a hypothetical strong dynamics through the condensation of some pair, you now achieve with the condensation of an elementary scalar, which you could do it with coupling.
You mean use? I think I see what you're saying. You mean using this sort of complementarity idea?
I don't even need complementarity. I'm doing everything at weak coupling. Everything that people do with complementarity, you can do with weak coupling by just throwing in a scalar with the right quantum numbers.
So the quantum numbers is it's bifundamental under.
Well, whatever quantum numbers you had you wanted to postulate that some bilinear fermions condense. That's what you wanted to postulate, and that was a dynamical assumption, that some fermion bilinear condenses. So whatever quantum numbers this bilinear has, throw in a scalar with exactly these quantum numbers, and then tune a potential for that scalar for it to condense. So this doesn't mess with the symmetries. This does not prove that the strong dynamics really happens, but it shows that somewhere in the parameter space, you can find the phase that you want. And that's all you need, because you don't care about the dynamics, the strong dynamics. So all I'm saying is that you can achieve the same thing without the assumption about the strong dynamics.
Yeah, thank you, Natty. I'll have to think. I can see what you're saying. It's a great idea. I'll have to think about it to make sure there's no pitfall. But I'll think about it and get back to you after the talk. But thank you. Yes.
Hi, David. What do the scalars, the Higgs fields for H in the top right of this slide do?
Oh, all they were there for was to make sure that I could decouple all this auxiliary stuff should I wish. But to gap everything, I don't want to decouple it, so I just give them a large mass and forget about them. So they're not playing a role in anything below the fact that they're there.
David, in terms of this UV, your original theory is asymptotically free, right? You started from the. So when you are saying that you have this UV Lagrangian, I mean, I'm not sure that I follow the point that in this way you are not breaking asymptotic freedom of original theory or by this term or not, because the term itself is UV. I mean, it gives you very different UV behavior, right? So. And it's related partly to what Natty said, right? Because when you're doing with scalars, then you're not breaking this.
I didn't understand, Arkady. I'm really sorry.
No, you added this UV Lagrangian, this 4 fermion, right? Lambda, psi, chi.
Oh, so the 4 fermion term is bad in the UV. It's an irrelevant term, so it does grow in the UV, but it also grows in the IR. It's dangerously irrelevant.
No, I agree, right? But in this way, if I'm considering short distances, then it's very different behavior if I indeed would add such a term, right?
I see what you're saying. I'm going to imagine there's a cutoff. And the key is that everything's weakly coupled at the cutoff, including the coefficient of this 4
Yeah,
fermion.
okay. So you are seriously changing UV behavior of the theory in this sense, right?
Not at the cutoff, but
yeah.
If you insist on going beyond, yes.
Yeah, I see. Okay.
Someone scribbled on my screen. Could you delete that that yellow line, please? let me give you example number 2, which is going to proceed very, very similarly until thank you very much, until right at the end. So example number 2 is, as you can see, very similar. It's SUN with an anti-symmetric and a bunch of fundamentals, fewer fundamentals now. And we proceed as before. We introduce a bunch of singlets under G, some fermions that are singlets under G, and then we gauge this H equals SUN minus 4 symmetry. We also add these scalars so that we can decouple everything, should we wish. All right. What we have now is very similar to what we had before, but the roles of the symmetric and anti-symmetric have been reversed. So the gauge field now has a symmetric with a bunch of fundamentals, and the guy chi, which is in the anti-symmetric of G, is the thing that's sort of standing by until the very end and not playing a role in the dynamics.
David, question here from Max.
Yeah, please.
The additional fermion, should that be in the anti-symmetric bar?
No. No. So what have I got? I've got no. I've got SUN minus 4, but with coupled to n fundamentals. So there's 4 more fundamentals than the rank of the gauge group. Not quite the rank minus 1. And so the way you cancel the anomaly in H is you need a symmetric. It was an anti-symmetric in the last one, if I just go back. And in this case, it's a symmetric.
I see.
So now we again have a strong coupling question. It's a gauge field coupled with a symmetric representation and a bunch of fundamentals. Again, it's been studied. Here, again, we're fairly sure we know what happens, but I would say with less confidence than the previous example. Again, there's a conjecture that this confines in the infrared, but without breaking the chiral symmetry. It doesn't break the chiral symmetry, and therefore it has to reproduce the Toft anomaly. And it does so again by forming a composite. The composite is now in the anti-symmetric of G. So things sort of sound very similar. It's a nice simple guess, but we don't have the complementarity argument that we used in the previous case. And in particular, if I understood Natty correctly, that means that we don't have the option of thinking of some weak coupling version about how to do things in this case. We really rely on this strong coupling dynamics and this confinement to make it work. Now, if this is the behavior of the theory, we can do exactly what we did before. We can add a 4 fermion term, which then gaps everything, preserving preserving G. There's a large n argument that this must happen at suitably large n, but we know it breaks down. And I don't know where it breaks down, but by the time you get to H equals SU2, I claim this behavior here does not happen. And I'm going to explain why that is, which means that to gap, say, fermions preserving a G equals SU6 symmetry, we're going to have to find something else to do. Let me explain why I think this doesn't work when H is equal to SU2. And it's a technical issue, but it's a technical issue that will be important down the line. When you've got a G equals SU6 with just 2 fundamentals, the gauge group you're introducing is SU2. It's SU2 with 6 doublets because we're SU6, and the extra guy introduced, the symmetric, is just an adjoint for SU2. Now, in contrast to all the other strong coupling gauge theories I've discussed, this is a vector-like theory. This is not a chiral gauge theory. The adjoint is a real representation, so I could easily just give a mass to that. And the 6 doublets of SU2 are really, because the fundamental is a pseudo-real, are really 3 Dirac fermions. So I can give a mass to those as well. The fact it's a vector-like theory is very likely to change the dynamics. Let me explain why. There are now 2 possibilities, each of which is very natural, a priori, for what happens. It's quite possible that this SU2 theory confines without breaking the SU6 symmetry. And it can do so by giving rise to a massless composite fermion, just as before. However, a novelty is that for this one, we can introduce a psi-psi scalar, which is gauge invariant under SU2, but could quite possibly condense, and if it condenses, breaks the SU6 global symmetry that we care about. And so the question is, which of these two happens? And I claim, indeed others have claimed before me, that the second option is the thing that happens rather than the first. So let me tell you the argument for that. The argument goes back to some beautiful work by Weingarten in the 80s, and in this particular context that I'm discussing here was shown, I think even for this example, in a lovely paper by Ofer and company in the context of breaking supersymmetry of n=1 theories back in the 90s. There's a lovely appendix, which I suspect was written by Michael Peskin. I'm not entirely sure about that, but that's where you can find this result. Let me tell you the result. Back in the 80s, Weingarten has a beautiful paper where he proves that the proton is always heavier than the pion, which you might think is obvious because the pion is a Goldstone boson, but the crucial fact is he proves it without assuming chiral symmetry breaking. In fact, he proves it using techniques of that Waffer and Witten introduced at the same time. The papers came out simultaneously. Waffer and Witten introduced to prove their famous theorems. So let me just give you a sketch of what this Weingarten inequality of masses looks like when applied to this SU2 theory. So the idea is the following. You look at this composite fermion, this 3 fermion state, and you look at the propagator of this 3 fermion state. And the propagator is the following. So each of these S's is the propagator for one of the composite quarks, but it's the propagator in the background of a particular gauge configuration. Okay, so it's a complicated object. And then the integral you do, which looks very simple because I've just written integral d mu, is the hard part of the exercise. The integral you do is you integrate over all gauge configurations together with the contribution from the fermions, which is the determinants of the Dirac operator. Now, the key to the Weingarten inequalities, and indeed the key to the Waffer-Witten theorems, is that this integration measure is positive definite. So this is something that you only get because the theory is vector-like. Chiral gauge theories have non-positive definite measures. This vector-like theory has a positive definite measure, so it's only in this case you get to use these arguments. All right, now if the mass of this state is m subscript chi, you expect that at very large distances, this propagator goes as e to the minus the mass times the distance. Now, the Weingarten inequalities are very straightforward. They're basically, the first is Cauchy-Schwarz-like inequality, which I'm embarrassed to say it's all to do with the flavor and the spinor and the color indices that I've hidden here, but it's of this rough form in the first line. And then the next step is what's called the Holder inequality, which is an even fancier Cauchy-Schwarz inequality for positive definite measures. The upshot is that you write this propagator in terms of something that you recognize as the propagator for the pion field, together with something else which is at most a constant, from which you get, this goes as e to the minus the mass of the pion, and from this you deduce that the mass of the scalar, the 2 fermion bound state, is always less than or equal to the mass of the fermion, which is the 3 fermion bound state. In other words, in this example here, if this fermion were massless, the scalar would be massless as well. But why would a scalar be massless? The scalar is massless because something's condensed. The symmetry group is broken and it's a Goldstone mode. So it seems very likely, based on this argument, that the case of SU2 doesn't work because the symmetry group gets broken. It plumps for the spontaneously broken phase rather than the confined phase. Any questions about this? All right, so this brings me to the situation that we actually understand very well. There's a way out. Take this particular theory, SU2 with 6 doublets and an adjoint fermion. As I've just argued, if you don't add anything else, the theory is very likely to break the SU6 symmetry. That's game over for gapping fermions preserving this. However, if you take this theory and you make it supersymmetric, which is fairly straightforward, it means adding 6 scalar fields in the fundamental of SU2, and then adding very specific Yukawa terms between those and the adjoint Weyl fermion. It has n=1 supersymmetry. Among the many interesting properties of n=1 supersymmetric theories that Natty Seiberg found in the 90s was that this one in particular has the property that it confines without breaking the SU6 global symmetry. It's exactly what we want. But by the way, you could ask, how do we avoid the Weingarten argument? It's because as soon as you have scalars and Yukawa terms, the measure is no longer positive definite. The Dirac operator d/+m is positive definite only if m is itself positive because of the zero modes from d/. So a Dirac operator d/+phi, where phi fluctuates positive and negative, is not positive definite. So the Weingarten inequalities don't apply. And in fact, it's an example that we know of confinement without chiral symmetry breaking. But now one where we're really sure that this is the dynamics that happens, because we have supersymmetry. So we have a lot more power. There's a lovely paper by Chabachaki, Martin Schultz, and Vitek Skiba from a couple of years later. They have a whole list of theories, supersymmetric theories, that have this property. They confine without breaking their chiral symmetries. All right, let me show you what we can do with this. So the final example that I told you I wanted to do was the standard model. Let me show you how you can gap one generation of the standard model without breaking SU3 times SU2 times U1, which you can think of as a global symmetry or think of as the gauge symmetry of the standard model. All right, so here's one generation of the standard model. I haven't included the right-handed neutrino because it's a singlet. I can just give it a mass anyway. And the one thing to note is that the left-handed fermions I've conjugated so that I've turned them into right-handed fermions. You can see that here, for example, the quarks transform in the 3 bar rather than the 3 of SU3. All right, so following the kind of steps I did before, there's now 3 steps that will gap all of these, preserving G. Here we go. The first thing is we need to add some new fermions. And one of the differences from what I did before is that we need to add fermions that themselves are charged under G. Previously, all the additional stuff was singlets under G. We need to add fermions that are charged under G, but they're in vector-like representations. So we could, if we wished, give them a mass and decouple them. You can see that the 3 comes with a 3 bar. The hypercharged quantum numbers are flipped. In addition, I've also added 2 singlets, 2 right-handed neutrinos, if you wish.
David, your division to left-handed and right-handed, no, in some sense, is conditional, right? Because you can talk about all left-handed. So what is your principle? Why you divide it this way?
Just to keep everything right-handed on the board. There's no real reason. I think it's just simpler to view things in this way.
I see. Okay.
All right. The addition of the extra fermions gave me the symmetry H that I wanted. You know, the previous examples, I just told you the fermions that transformed under G, and there was an obvious H sitting there. With the standard model, that's not the case until I add these extra fermions. But once I do, you can see that very clearly that I've added them so that the first line and the second line have the same quantum numbers, and there's an extra H that's been introduced into the game. What I would have here is H coupled to 6 doublets. There's 2 here, there's 3 here, there's 1 here. That's not a theory that confines without breaking chiral symmetry, but as we've just discussed, we know how to change it so it does. I just supersymmetrize everything that's here. So for H, that means in particular I add an adjoint Weyl fermion under H, singlet under G, and then I add a bunch of scalars, super partners for everything that's here. Now we're done. So we use the result of Natty that this particular SU2 supersymmetric gauge theory confines without breaking its chiral symmetry. It's an SU6 chiral symmetry of which G, the standard model, is some subgroup. And what does that mean? It means that in the infrared, everything in a green box pairs together into a meson field. A meson field which is a singlet under SU2. Now there's 6 doublets in the green box, And the pairing is such that there's an anti-symmetry. So the number of mesons you get in the infrared is 15. It's 6 times 5 divided by 2. So it's all the different pairs that I've written at the bottom of the screen here, where I've given names to what are now superfields for each of the particles. All right. If you look at the stuff that was a bystander, look at the stuff that wasn't coupled to SU2. These are the things outside the green boxes. There's also 15 of these fields. There's 2 plus 6 plus 1 plus 3 plus 3. And the lovely fact, which we've seen in the previous examples, is that the quantum numbers of the 50 mesons at the bottom of the screen are precisely conjugate to the quantum numbers of the bystander fields that weren't involved in the strong coupling dynamics. In particular, that means if I go back to the UV, I add this cubic superpotential. So now it's a Yukawa term in UV, it's not a 4-fermion term. Nonetheless, it's marginally irrelevant in the UV, but as we flow to the infrared, the first 2 fields in each of those terms pairs up, it confines, it acts as a single field in the, each of them acts as a single field in the infrared, and this cubic superpotential becomes the quadratic superpotential at the bottom. It preserves G, but clearly everything gets a mass. So once again, it's an example where we've gapped all the fermions in one generation of the standard model without breaking electroweak symmetry. It would be very nice if there was some phenomenological application of this. I can't think of any, but obviously it would be very cute if somehow there was.
Is the supersymmetry still present in infrared?
It is, but it's possible to break once you're in the infrared. Yeah, you could certainly start splitting the scalars and the and the fermions. All right, this is the end of the first part of my talk. This is 90 minutes, Juven. Is that right? Because I could just stop now, and this is the end of how you gap preserving global symmetries. But the last part was to talk about how this might be useful for chiral.
You have 30 more minutes.
All right, but this is a good time to stop and ask questions, because the next 30 minutes is going to be a little different in spirit.
So do you expect that this is always possible or sometimes possible? When do you think you can find such an example, such a construction?
There's a little bit of an art to it, where to be honest, the art is mostly going through this lovely paper of Chabachaki and just looking at all their examples and seeing what I can do. I have found some examples that I tried and failed. Let me give you one. If you add the right-handed neutrino to the standard model, there's also a B minus L that's non-anomalous. And so I tried to find a way to preserve gap 16 fermions, preserving not only the G that's written at the top of the screen, but also B minus L. And I failed. My suspicion is that I wasn't smart enough. My suspicion is that, and I don't know of any obstacle towards doing this. So there are things I can't do, but I suspect others could.
Excuse me, David.
Yeah, please.
Yeah, von Schuben. So my understanding is that example 1 and example 2 still have some uncertainty about the dynamics, assumption about dynamics, even though you say probably people believe it's true, but it's not very rigorously shown. Well, the last example 3 is more control because of supersymmetry. Is that right?
The last example is on much better footing. That's right. And there are many more examples that I know of using supersymmetry, because there are many examples that have this property that we can cook up. Yeah.
Okay.
But what about what you think? It's returning back to what Nati was asking about this additional scalars to make it more visible.
I'm not good enough to think on my feet, I'm afraid. So I don't know, but I'll as soon as the talk's done, I'll investigate that. It does sound interesting. It works only for example 1, what Nat is suggesting, because it sort of relies on this complementarity. It wouldn't work for example 2, and I certainly don't know of a way to gap the standard model while without at weak coupling without breaking. G.
Okay, thanks.
David, quick question.
Yeah, please.
So could you give us like a intuition? What does the supersymmetry magic involve?
the thing it really gives us is the ability to solve the theories. I could well imagine that. So I think there is a lesson here, which is that vector-like theories with positive definite measures don't do what you want to do. I think there are sort of Weingarten-like arguments against that. But the scalars are sufficient to avoid the Weingarten arguments. Scalar doesn't necessarily mean supersymmetry, so I could well imagine there are other models that do this, but it's all strong coupling, and we're not good at strongly coupled theories without supersymmetry.
But so with supersymmetry, what is the actual trick that lets you solve?
I'm nervous arguing this with Natty in the audience. And holomorphy, really, it's the fact that things like these superpotentials are holomorphic objects, and that greatly restricts the kind of behavior you can see.
Maybe let me.
I have a question. The example, you said that there's an obstruction to using this trick with the scalar when complementarity does not apply. But whenever complementarity does not apply, the modern perspective of that is that the system has a one-form global symmetry. So I'm curious whether in your set of requirements of what you do or do not want to preserve, you took that into account. More generally, my hunch is that if you take that into account, whatever you could do with strong coupling in that phase, you could do the same thing with weak coupling. Weak coupling a bit with different fields.
That would be very interesting, obviously. So here was my understanding, and it could be wrong, that there are two possibilities for the strong coupling. One is that chiral symmetry is not broken and there's a massless fermion, and the other is that chiral symmetry is broken. And whenever you try to achieve that at weak coupling, you always find the latter. You always find that the symmetry breaks precisely because the scalars that you introduce typically transform under that G. But as you pointed out, the kind of thing that happens in complementarity may be achievable just by a scalar. I don't know, Natty. I don't know, but it should be very easy to check. All right. If there's no more questions, I'll just make a few comments on this big problem of putting chiral fermions on the lattice.
Maybe.
Yeah, please.
I think you mentioned you add a scalar superpartner to all the fermions in the previous example 3, right?
I didn't quite understand what you said.
You say you add this scalar superpartners to all the fermions in the last example. And where do I see them?
They're buried. They're buried. These capital letters are superfields. So by the time and what I've written down here is a super potential. So I'm sorry, I buried them in some supersymmetric notation. Yeah. But
you say scalar superpartner, right? In your previous line, maybe.
That's right. Everything that's a capital letter here is a scalar plus a superspace parameter times a fermion. So they're hidden in the notation, I'm afraid.
Okay. Thanks.
All right, let me move on and shift gear a little bit. So, as many people in this seminar series have discussed, there is a very important open problem, which is how you simulate chiral gauge theories. And there's a no-go theorem, famously the no-go theorem of Nielsen and Nemir, which puts up certain hurdles, barriers, if you wish to do it. And the essence is that if you try to put a single Weyl fermion on the lattice, then the lattice will rebel, and it will give you back a fermion of the opposite handedness. So I guess here on the left, I've put the Brillouin zone for a one-dimensional object. You try to put a single left-moving fermion at the origin. The energy has to be periodic as a function of momentum. The momentum itself is periodic because it becomes the Brillouin zone. And so what goes up has to eventually come back down and cross the axis, and you find that you get a doubler, which is a fermion of the opposite handedness or opposite direction in 1 + 1 dimensions. A very beautiful idea due to David Kaplan that I'll talk about a little later is that you can somehow not split these doublers to some extent in momentum space, but you can instead split them in real space, where the real space is an extra dimension. So alternatively, you can consider a 5-dimensional massive fermion on an interval. You get a left-handed fermion here on one end of the interval, but the right-handed fermion makes an appearance on the other edge. And there's a very old idea that dates back to this really, I think, very interesting paper by Eichten and Preskill, that if you want to put chiral fermions on the lattice and chiral gauge theories, what you have to do is find a way to give a mass to the unwanted mirror fermions, to the doublers. So if you're in the momentum space language, you have to find a way to give a mass just to the fermions that sit at the edge of the Brillouin zone. But in doing so, you shouldn't break any of the symmetries that you care about. In particular, if there's a gauge symmetry or a global symmetry floating around, you should give a mass to a bunch of fermions without breaking that symmetry. On the domain wall picture, you have to give a mass to the fermions that sit just on the right-hand edge. Make sure the left-handed ones stay massless. So there are some challenges in this approach. There are many, but I'm going to flag up 2. One of them is that whatever interactions you introduce to gap the fermions, you've got to make sure that only the mirror fermions experience it. Only the doublers that you don't want feel that interaction. But the original ones, either at the origin of the Brillouin zone or on the left-hand edge in the domain wall, they're immune to the interaction somehow, so they remain massless while the other ones become gapped. Secondly, you better make sure that whatever interactions you introduce do the job that you care about, which is that they gap the mirror fermions without breaking these symmetries. Okay. So Eichten and Preskill had a very interesting idea. They suggested that you should add on the lattice some 4 fermion terms. Now, as I mentioned before, 4 fermion terms are irrelevant in the continuum, and so can't possibly gap a bunch of fermions in 4 dimensions in the continuum. However, on the lattice, you can do things that you can't on the continuum. You can take an irrelevant operator, you can crank up the coupling so that it's strongly coupled at the lattice scale, and the hope being that strong coupling at the lattice scale will do what you want. It will gap the mirrors, leaving the other ones behind. There have been a lot of attempts of variations on this theme. I've listed some of them on the bottom. I'm sure I've missed people, and I apologize. Eric Poppitz and collaborators have a very interesting collection of papers applying this to overlap fermions. Kikukawa has a very interesting paper on SO10. In particular, papers by Xiaogang and subsequently Xiaogang and Juven have various versions of actually both of these, which I think are very interesting. Nonetheless, I think so far it's true to say that nothing has been proven to work. And there are some things out there that haven't yet been proven to fail, but certainly whenever anybody has attempted to simulate using this, it just doesn't work. Either the symmetry gets broken by the interactions, or you end up gapping both of them, or you end up not gapping the mirror fermions. So I think it's a true statement that this remains an unsolved problem, certainly at the level of simulation. Xiaogang, do you have a comment?
I
You've
think
suddenly lit up
for the numerical simulation, I think we don't have anything firm, because this very high dimensional theory so it's hard to say. But I do not agree your calculation that this approach does not work. Actually, there is a 1 + 1D model which one can do go a little bit further. I think that for this 1 + 1D case, one can show this idea actually can work. But however, for 3 + 1D model, there is idea and there is construction. But however, as you said, involving some kind of strongly coupled system. So one need to numerical calculation to confirm the proposal. But this numerical calculation, I think, is maybe too difficult. May have a sign problem, so it's not been done. It's very hard to do. So that's indeed there's no numerical confirmation. Yeah.
And it clearly has a sign problem, as I'll discuss as we go on. So the question I'd like to ask is, we now have, as I've explained at the beginning of this talk, some very simple theories that do the job of gapping chiral fermions, preserving the chiral symmetry, but in the continuum. So we wouldn't have to rely on any strong coupling mechanism at the UV cutoff. Everything can be weakly coupled at the lattice scale. It'll flow to strong coupling in the infrared and do the job for us. So the question is it possible just to adapt this and use it for the lattice? I should also mention that there's a sense in which Xiaogang and Juven's paper, the one that Xiaogang just mentioned in 2D, does something similar. So it's worth maybe just highlighting this. Xiaogang and Juven look at a 1+1 dimensional model where you should be able to gap by introducing 6 fermion terms. Now, a 6 fermion term is irrelevant in 1+1 dimensions, but for free fermions in 1+1 dimensions, you also have marginal interactions, which are current interactions. So they're 4 fermion terms. And it's possible to dial those marginal interactions up so that the 6 fermion terms actually become relevant. So you don't say this explicitly in your paper, Xiaogang Juven, but I'm pretty sure you understand it, because I'm pretty sure that was underneath what was going on.
That's exactly, you're very accurate. That's exactly what we do. For certain, around a certain free fermion point, those fermion coupling are irrelevant. But you can dial this marginal direction to make those fermion coupling relevant, and then one can show that this relevant part only in some subsector of theory. Other part is not coupled. Then the subsector theory, this relevant operator can be boson line map to sign Gordon theory and then show that part is gapped without breaking any symmetry. So in 1+1D, one can play this kind of trick. Indeed, you're very accurate.
Exactly. So I think what I'm suggesting here is really what you did do using multi-fermion and marginal operators in 1+1 dimensions. The question is, can we do something in 3+1? I'm not going to solve the problem.
Yeah, that's maybe hard, yes.
Yeah, but I'll just make. I've only got 10 minutes, but maybe I'll just make a few comments. So here's the idea. Take domain walls, and I should add, firstly, I'm going to talk about domain wall fermions in the continuum, because you can talk about domain walls on the continuum. They came from Callan and Harvey originally. And then I'll compare that to the kind of things that people have been doing on the lattice. So in the continuum, we take an interval for the fifth dimension. Take the gauge theory that you care about and put that everywhere. So it's a 5-dimensional gauge theory that looks 4-dimensional at low energies. And couple it to some chiral fermions that you care about. But so the chiral fermions you want are on one edge and the conjugates are on the other. So actually, you've now got a gauge theory coupled to a vector-like theory. It's not what you want, and we're going to have to try and gap the ones on one edge. All right, next step. Add this auxiliary gauge field H. We're going to put that everywhere as well. It's also going to couple to chiral fermions on both edges. And the final step, I guess I've got 2 steps here, and logically I may have put them in the wrong order, but the final step is simply to turn on a Higgs field for H so that it removes H from the dynamics on the left side of the domain wall, but keeps H active on the right side. So I've got this slice that has previously been called a waveguide in the literature. I'll stick with this. So the waveguide is this yellow region. There are 4-dimensional gauge dynamics for H taking place in the yellow slice, the kind of gauge dynamics that we've just been talking about. And the goal is that those gauge dynamics are going to gap everything on that slice, leaving the things on the left behind. All right. So what goes wrong with this? This is the question that I'd like to ask. So what are the pitfalls? So the standard things you should ask when doing lattice gauge theory, at least, is what would happen if the theory were if the symmetry were anomalous? Because the lattice doesn't know anything about anomalies, but typically whatever would happen if there was an anomaly is what does happen, even if there's not an anomaly. So let's ask these questions here. What happens if the chiral fermions are in an anomalous representation of G on one edge. Well, then it's very simple. You can't possibly gap them on one edge while preserving G. That's one of the prerequisites. So we'll take them to be in a non-anomalous symmetry of G. The next question is, what if their chiral fermions are in an anomalous representation of the gauge symmetry H? That's going to be worse because we've got chiral fermions here coupled just to H, but H doesn't know about the ones on the other side because we've Higgsed it. So what happens in that case? Well, in that case, if the theory on one edge is anomalous under H, then the full 5-dimensional theory will have a Chern-Simons term for H because it's the same sum of triangle diagrams that one has to do in both cases. So if the theory on one edge is anomalous under H, there'll be a Chern-Simons term with some coefficient K that captures the anomaly in 5 dimensions. Now, because of the presence of that Chern-Simons term, when you Higgs, you don't quite decouple the Higgs field. In fact, you don't decouple the phase of the Higgs field. What happens is where the Higgs field has its profile, you'll end up with a Wess-Zumino term that sits there. The Wess-Zumino term is necessary in order to capture the anomaly of H. So sitting on this orange slice, which is where the profile of the Higgs field was, you'll get a Wess-Zumino term of this form where omega is a group valued element in H. It's like an axion field, non-abelian axion field. And by the anomaly, the 4-dimensional anomaly, you can rewrite this term as a coupling between the fermions and the derivative of omega that sits there. However, if you had what you wanted, which is a set of fermions on the edge which were not anomalous under H, then this Chern-Simons term vanishes, and there's no such dynamics on the wall. In fact, the interface where the profile of the Higgs field changes is nice and smooth. There's no light degrees of freedom that live there.
Excuse me.
Yeah, do.
So you mentioned that if the fermions has the anomalous symmetry in G, then maybe you cannot gap them. But even if so, if the anomaly is a global anomaly, and for certain kind of a global anomaly, you still can preserve G, but gap, but just develop this TQFT topology. That's also
for discrete symmetries. There are much more interesting things, and I'm just going to brush all that under the carpet.
no problem. Thank you.
All right. However, there's another pitfall. As we've seen in the examples, typically when you gauge the symmetry H, you have to introduce some extra fermions, possibly extra fermions to cancel the anomaly of H, or possibly things like the extra adjoint fermion when H was SU2, just to make sure that the dynamics does what you want, which is flows to confinement without chiral symmetry breaking. So we've seen there are two categories. One category is when H is a chiral theory, and the other category was when H was supersymmetric, because then I can solve it. Now, what happens? I introduce these extra fermions for H in the same way that I introduced the originals. In other words, some of the extra fermions for H that I care about are on one wall. That's this one, but I'm always going to get the doublers that sit on the other wall. Now, what happens with these two options? If H is a chiral theory, I need to add new chiral fermions to cancel the anomaly. I have some here, but I get new ones that sit on the other wall. And then I've kind of got myself in a vicious circle because I've got some new chiral fermions that I've got no way of gapping because they're chiral. So I think the cases where H was a chiral theory does not work. However, when H is vector-like, and in particular supersymmetric, the extra fermions that appear on the left are not chiral, they're vector-like. You can simply gap them with a Majorana mass. So in this case, in the continuum, there's nothing that stops you setting up the H gauge field living on one half of the interval, gapping everything on that wall completely, and leaving behind just the chiral fermions that you cared about with this symmetry group G. So the standard model coupled to one generation, for example. So there's no problem doing this in the continuum, provided the anomaly for H cancels. And moreover, there's no problem to discretizing all of this so that you get the theory that you want on the lattice, things being weakly coupled at low energies. there are problems to simulating. There are very serious problems to simulating. In particular, recall that the vector-like gauge theories that did the job could not have a positive definite measure, otherwise you could use Weingarten inequalities to rule out the behavior that you want. But not having a positive definite measure is a killer for Monte Carlo simulations, because it means you necessarily have a sign problem. And in fact, I think in 4 dimensions, any attempt to put a chiral gauge theory on the lattice will have a sign problem, because the partition function for the chiral gauge theory has a phase. You know, it's not a positive definite partition function, so you're always going to run into this problem. In addition, there's significant fine-tuning, because we've got a supersymmetric theory which we're trying to put on the lattice. What I'd like to do in the last 3 minutes is just compare this attempt to look at domain wall fermions in the continuum with what people have done on the lattice, because this has been explored on the lattice. So let me walk you through this. We take a single 5-dimensional Dirac fermion, we give it a mass, and we put it on an interval, but we discretize the interval. We're also going to discretize the extra 4 dimensions of space-time, but I'm going to ignore that for simplicity. So what do we have? Well, we have the 4-dimensional kinetic terms for the two component objects. We have the 5D hopping terms, and if you tune the Wilson parameter to be 1, the hopping terms take this nice zigzag form, sort of form. And then there's the mass. So it's very simple to show that if the mass is positive, you get a left-handed zero mode here. Roughly speaking, it's this first chi. And you get a right-handed zero mode here. Roughly speaking, it's this last lambda. Of course, there are profiles that are exponentially suppressed. So this is really just the beautiful idea of David Kaplan and the slight variant by Shamir from a year later. All right, now comes the difficulty. You want to add a gauge field that's localized just on one edge of the interval on this waveguide. In other words, all the fermions that are yellow dots, you want to turn into gauge fermions that transform under a gauge symmetry. And all the ones on the left that are gray and blue dots, you don't want to transform under the gauge symmetry. The problem comes in the hopping term between the two, because the hopping term, as you can see here, links this lambda to this chi. So these are the ones that I've called star, but is not gauge invariant, because this one transforms under the gauge symmetry and this does not. So to proceed, you're obliged to introduce on this link a new dynamical field, which is group valued in H, and the hopping term becomes a Yukawa term of the following form, where omega is, well, as I said, group valued in H. Now, as we've just seen in the continuum, this is not a surprise, because this is exactly the West-Zumino term that one expects to get on the domain wall. It's only absent if you have a collection of fermions for which the anomaly cancels. But here, and certainly in the papers listed at the bottom here, people just looked at a single fermion. So of course there's this new Yukawa interaction that has to be introduced there. Moreover, the upshot of these papers, these are papers from the 90s, and really the papers that people nod to when they say that this approach of putting sort of gauge fields just coupled to one edge of the fermions doesn't work. They came to the following conclusion. They came to the conclusion that it was impossible to remove this field omega. And in addition, it was impossible to remove these two fermions that were the neighbors. These always remained light. The upshot was that you end up with a vector-like spectrum coupled to the gauge field, because there was the light mode on this edge, but this now couples to a second light mode on this edge. So this was seen in some analytic calculations, which, because of time, I won't mention. And importantly, it was seen in quenched simulations. They were obliged to do quenched simulations because non-quenched simulations come with a sign problem, and you run into problems. The trouble is that quenched simulations ignore the fermion loops. Fermion loops are crucial. Fermion loops are the thing that gives rise to the Chern-Simons term in 5 dimensions. and the thing that's going to tell you that this omega field ultimately decouples. Moreover, as we've seen, this approach has to have a sign problem because things that don't have a sign problem can't possibly give rise to chiral gauge theories. So actually, if you look at the expectation from the continuum and what's seen on the lattice, my interpretation of this is that this approach will work, but has a sign problem. I don't think the evidence they have is any evidence at all for this approach of trying to couple gauge fields on one edge not working. It's just that they haven't asked the hard questions, because the hard questions are hard. The hard questions are to do with a sign problem. So very much in the spirit of what Juven and Zhaogang were saying, I think it is possible to use this approach to put chiral fermions on the lattice, but it's going to be very difficult to simulate numerically because you have to somehow get past this sign problem. So what I want to sort of speculatively suggest is that the problem of fermion doubling on the lattice is not really any different from the sign problem. What we think is a deep problem of putting chiral fermions on the lattice at the end of the day is really the same as a sign problem, and that sign problem is unavoidable moving forwards. All right, I've gone over time a little bit, for which I apologize, but thank you very much for listening.
Thank you.
Thank you, David, for the wonderful talk, and thank you for being a kernel bridging between high energy and the condensed matter physics. Question from the audience, please.
May I ask you, David, you know, from the, I don't know, maybe it's kind of almost irrelevant question, but still, let's say I am looking from continuum side, I mean, not from the lattice. The problem with chiral fermions I can formulate them without referring to the lattice as a problem that if I try to introduce regulator fields in Lagrangian form in the theory to make you know, kind of effective cutoff of the theory with the help of regulator, I cannot do it with this while fermion. I mean, so I do not know how to introduce regulators, right? It's another way of saying instead of Nielsen-Ninomiya theorem, you can see that this is not possible. On the other hand, when you in your previous example, you know, in particular with having in mind this comment by Nati, you know, it could direct me to think about possibility to still do it with this additional field, but in form of introducing regulator fields. You see what I'm trying to say? Is that trying to use your type of construction and maybe even this additional scalar field to make explicit regulator sectors, and then it would be an answer, right? Because if I will manage to do it, I mean, okay, I'm sorry that maybe it's irrelevant, but still I'm trying to.
You've beaten me to it, Arkady. So I did indeed wonder if, you forget about the lattice, could you just use these techniques as a regulator, a perturbative regulator for chiral gauge theories, which I think it's probably a true statement that we don't have. People do it, but I think they do it by kludging things. And I thought the answer was no, because all of my techniques work at strong coupling. But if what Nati says is right, that there's weak coupling versions, that might well be that we can just use this as a perturbative regulator for chiral gauge theories. That in itself would be, I think, quite nice.
Yeah, so you do not think it's possible?
Right? No, I think it's very interesting. I think it's very interesting.
Any more question, comments? Please feel free.
No questions. I just want to thank David again for a wonderful talk.
Oh, thanks, Nati. That's kind of you.
Actually, there's a professor at U Tokyo, Professor Yoshio Chibukawa. He also worked on this domain wall fermion and this SO10. I don't know whether you have any comments. You are in the audience, since it's also related.
Thank you very much, Juven. I completely agree with Tom. The sign problem is a very big problem, and but recently there are some attempts to solve the sign problem using the so-called leftist symbol. approach,
Hmm.
and in which we complexified the field variables and change the integral contour to the complex region. And recently, Fukuma and Matsumoto of Kyoto University gave a very nice algorithmic approach, which can sum over the, which can perform the Monte Carlo simulation over the multiple left-set symbols. Yeah, usually if you consider the left-set symbols, you must consider several symbols contribute to the path integral, but they proposed a very nice approach to do multiple symbol simulations. So sign problem is very big problem, but we have progress. I think, yeah, and there is some progress, and we can apply such method to try to test the lattice models for chiral gauge theories. Although the numerical cost is rather huge, I guess, but there is some progress on this point.
Would be completely wonderful. Obviously, 1 + 1 dimensions is a good place to start. The theory of Juven and Xiaogang there.
Yes.
I had some conversations with Juven yesterday, and so it's maybe 2 6 fermion operators, but you need to break those down by introducing, Yukawa terms, Hubbard-Stratanovich things, so that you're computing the determinant of something. But then it does become complicated. It's a scalar-scalar interaction in the determinant.
Yes.
So but it would be wonderful if that could work. I also have some simple U1 gauge theories in 2 dimensions.
Yes.
Do the job in a more similar way to this.
Yeah. So we can start from the 2-dimensional case or 3-dimensional domain wall approach.
Yeah.
To simulate. Yeah.
Actually, I did try to communicate with people who are good in doing numerics using like DMRG or tensor network and try to simulate.
Yes.
Yeah. For some reason, they haven't been able to finalize the story. I don't know how difficult it is. Maybe they are just, anyway, it takes some time. It's like more than 20 years.
I have a very trivial comment. In 2 + 1, there is a rather simple way out of this problem to some extent. You can certainly give a mass to the doubler in that case at the price of breaking time reversal symmetry. And so now you have a Chern, it's a Chern number that the theory has. Certainly the partition function has a non-trivial phase factor because of that. And so it's complex. So there may be problems to the simulation, but certainly you can gap out the doubler without and tune the theory so that the leading fermion, the interesting fermion, is massless.
Sorry, Eduardo, can I just check? Are you talking to fermions in 3-dimensional domain walls?
In 2 + 1.
The domain walls with 1 + 1.
No. In 2 + 1, no domain walls. Okay. I mean, you can do something similar, I suppose, with domain walls, but let me just simply do the simpler case. In 2 + 1, you put fermions on the lattice, any fermions you want. Okay, and you can gap out the doubler at the price of breaking time reversal symmetry. Okay, or parity. In 2 + 1, they are the same. So it's true that the partition function is no longer real in that case. So it's true that there is all of these examples will have a sign problem, but you can certainly make one fermion massive and the other fermion can be made as light as you want.
That's true, but
this avoids the main question, because you cannot put a chiral gauge theory in 2 + 1 dimensions for this simple reason there are no chiral theories.
I know, so that's why I said this is a simple and perhaps trivial example, but it's not a question of your inability of killing the doubler. You can at the price of time reversal in that case.
But
it doesn't work in 4 dimensions.
It's played by time reversal in 2 + 1. The question then becomes, can you give masses to fermions preserving time reversal? And there's a mod 16 anomaly, and so it should be possible to give masses to 16 chiral Majoranas preserving time reversal. there are some simulations by Iyer and Chandrasekhar, I think, that suggest they've done exactly that. That there are some, I think, 4 fermion couplings that do give masses to fermions in groups of 16 that do the job, preserving time reversal. Excuse me, preserving time reversal.
Yeah, I just want to make a comment about this tensor network approach, which works very well in 1+1 dimensional space-time. But however, in 2+1 dimensional and higher, the tensor network renormalization have some technical difficulties. So if it works, it will not have a sign problem. But there's other problems, so we cannot really do it in higher dimension.
And you could not use domain walls, but something in 1+1 where the overlap or just the kind of terms you guys were writing down where it's just the things at the edge of the Brillouin zone that experience.
Yeah. That one, the 1+1 dimensional path integral can be simulated by tensor network. Even the one with the sign problem can be simulated, so that's okay. Actually, we examined this, but it's a number. Just we have too many species of fermion, so internal dimension of tensor became too high, which blow the computer. There's no technical problem. In this case, there's no technical problem. We just need a bigger computer. But however, if you want to simulate the 2+1 dimensional path integral, then there is a more intrinsic problem in tensor network. And but it's really wonderful if you can solve it. Then that'd be huge consequence. Yeah.
Yes.
All right. Well, thank you everyone for your comments.
Thank you, David, for the wonderful talk, seminar, and bridging the different community. Thank you very much.
No, you're very welcome. And well, happy holidays, everyone.
Happy holiday, everyone. See you next year.
Up in the new year.
Yeah.
See you. 2021.
Best to Alex.
Thank you.
Thank you very much.